Thank you very much for being here. I will start my talk and I will talk about soil organic carbon modeling for my PhD thesis, which is entitled Estimating Carbon Input Changes Required to Reach Policy Objectives in Increasing Soil Organic Carbon Stocks. So I will start with a bit of context. So we all know that human activities are the main cause of climate change. This picture from the IPCC report shows that global surface average temperatures have been rising since 1850 compared to average temperatures between 1850 and 1900, causing unprecedented warming compared to reconstructed temperatures in the last 2000 years. And if we zoom in, I don't know why it doesn't work anymore. Okay, sorry. So if we zoom into the last 2 centuries, you can see that human activities are the main cause of this warming. So I think the problem is where people come in, but I will just use my keyboard, it's fine. So to fight against climate change, the European Union has committed to cut by 55% its greenhouse gases emissions by 2030 until reaching carbon neutrality in 2050. And while a strong reduction of greenhouse gases emissions is the most critical action, it won't be enough. In fact, natural climate solutions will also be required in order to avoid the worst effects of climate change. This picture shows that natural climate solutions can provide up to 1/3 of the cost-effective mitigation, which is needed between now and 2030 in order to stabilize warming below 2 degrees Celsius. So what are natural climate solutions? Natural climate solutions are those land management practices that enable to sequester CO2 from the atmosphere by increasing natural carbon sinks. And these solutions rely on different sectors, for example, forestry, wetland preservation and restoration, and agricultural and grassland management. And all these sectors rely on one important element that we will talk about today, which is soil. So soils will be critical in the next years for multiple reasons. First, they are the largest carbon pool among terrestrial ecosystems, and as such, they represent the biggest potential to store carbon. Also, they store 2 to 3 times more carbon than the atmosphere, and this means that even small changes in the soil organic carbon pool can translate into significant changes in the atmospheric pool. And finally, soils are provide our food, for which carbon is an essential component. So based on these ideas, in 2015, the 4 per Mil initiative was proposed to promote practices that would enable to sequester CO2 from the atmosphere and put them into the soil. And the initiative mainly focused on agricultural, on the agricultural sector, because this is where there is a large potential for improvement. And the name of the initiative, 4 per Mil, comes from the idea that if we wanted to compensate for fossil fuel emissions, we would have to increase the soil organic carbon stocks by 4 per Mil per year, which is 0.44% per year. And while the total compensation of CO2 emissions from fossil fuel burning is unlikely, the initiative has been highlighted as a promising option to, on one side, reduce climate change, and on the other side, increase food security through improved soil qualities like water retention, soil fertility, and increased biodiversity. So in addition to its greenhouse gases emissions targets, the European Union has been suggested to also increase its cropland soil organic carbon stocks by 1 to 4 per Mil per year by 2030 from the recently set Mission Board for Soil Health and Food. So a question that arises is, are those soil organic carbon stock targets feasible under current agricultural management? So first, how do we increase soil organic carbon stocks? To increase soil organic carbon stocks, we can either increase the carbon input to the soil from adding plant material or other organic matter, or we can decrease the carbon output from the soil, for example, locally by reducing erosion or by reducing soil respiration. And many authors have shown that increasing the carbon input is the most efficient way to increase soil organic carbon stocks. So in agriculture, there are different practices that enable to sequester carbon in the soil and add or increase the soil organic carbon stocks. For example, the restitution of crop residues to the soil, the addition of organic amendments, and the implementation of agroforestry and cover cropping systems, which increase the biomass of the plants and improve soil qualities like water retention and reduce soil erosion. So in this work, we try to address the following question, which is how much should we increase the carbon input to the soil to reach a 4 per mil objective of soil organic carbon stock? And some recent works have already focused on this issue, either from a modeling or from an experimental point of view. For example, the works from Martin et al. And Riggers et al. In 2021, who assessed the carbon input required to reach a 4 per mil target at the French and at the German cropland scales, and the works from Colton et al. In 2018 and Weissmeier et al. In 2020, who assessed the feasibility of the 4 per mil under different agricultural management practices. And although all these efforts have been made to address this issue, an assessment at the European scale is still missing. So in this work, we fixed two main objectives to try to fill this knowledge gap. First, we try to define how quantitative targets of soil organic carbon stock can be calculated. And then we use soil organic carbon models to estimate the carbon input required to reach a 4 per mil target at the European scale. So, first of all, why is it important to define quantitative targets of soil organic carbon stock increase? So imagine that a policymaker may want to subsidize a farmer for implementing agricultural practices that increase soil organic carbon stock. Then they may want to monitor, report, and verify that the results are achieved. So let's take as an example the Feuchol experimental site, which is located in northern France, and where soil organic carbon stocks were measured over time, and some crops were rotated under different treatments in order to see the effect on the soil organic carbon stock. So here I plotted for the control treatment of the experiment, so a treatment where no additional organic material was added to the soil. I plotted the soil organic carbon stocks over time, normalized against the initial soil organic carbon stock level. So you can see that the soil organic carbon stocks in the control treatment were mainly decreasing with time. And also you can see that they can be correctly predicted by a regression line. So imagine that you want to implement an agricultural practice to increase the soil organic carbon stocks by 4 per mil per year for a period, for example, of 30 years. Then you can calculate this target relative to the initial predicted soil organic carbon stock. And in this case, you would have around 5 tons of carbon per hectare sequestered over the 30-year period. Another way to calculate the target is relative to the control treatment, so the baseline treatment that you are considering. And in this case, you can see that the target is very different because the soil organic carbon stocks were decreasing with time. So these ideas were already discussed by Susanna et al. And Pellerin et al. In 2019, who showed the different target sets depending on how we fix soil organic carbon stock targets. And these authors pointed out that the first approach, so the one where you calculate the target relative to the first year of soil organic carbon stocks, was to be prioritized because it puts the priority on soils that have decreasing soil organic carbon stocks. And this is in line with the land degradation neutrality objective of the UN. So in this first part, what we wanted to assess was if the additional carbon input required to reach the 4 per mil target calculated with the two approaches were significantly different from each other. And to do that, we collected data on 11 long-term experiments in France and one in Sweden, where soil organic carbon stocks were measured over time and where 33 exogenous organic matter treatments were added to the soil. So basically for each site, we had a control treatment, so a treatment where some crop was rotated and no additional organic material was added to the soil, and then one or several treatments where the same crops were rotated and some additional organic material was added, for example, from livestock manure or compost. And you can see here that the soil organic carbon stocks in the control treatment of these experimental sites were mainly decreasing with time. So here I'm showing the soil organic carbon stocks evolution over time, and the average decrease in these experimental sites was around 1% per year decrease, plus minus 0.5%, which is similar to the current situation of European croplands, which are decreasing by 0.5% per year in the last decade. So what we found was that when additional carbon input was added to the soil organic carbon stocks increased with time. And in particular, we found that the majority of treatments of exogenous organic material reached the 4 per mil target calculated either by the first approach in blue here or calculated with the second approach, which is the one that is calculated relative to the control treatment. And what we found was that the group of treatments that used that reached the 4 per mil target calculated with the first approach used additional carbon input that was significantly higher compared to the group of treatments that only reached the target calculated with the second approach. And this difference was as high as 1 ton of carbon per hectare per year on average. But what we found was that not only the quantity, but also the quality had a significant effect on the soil organic carbon stock. And so for that, following the work from Levava et al., we defined the quality of the carbon input as the retention coefficient value of each exogenous organic matter input, where the retention coefficient was defined as the proportion of exogenous carbon that is not mineralized within 1 year. And what we found was that the carbon quality, as defined, had a main significant effect on the soil organic carbon stock variation when this was calculated relative to the initial soil organic carbon stock. And we found that there was a significant interaction effect between the carbon quality and the carbon quantity, no matter how we calculated the soil organic carbon stock variation. And so this result suggests that the carbon quality of the carbon input as defined by its retention coefficient can be a predictor of the soil organic carbon stock variation at the decadal time scale. So these results are important to keep in mind in order to reach the mission goal for soil health and food targets, because as I said before, soil organic carbon stocks in European croplands are decreasing, and this may require significantly different carbon addition according to how the target is set. However, we found that also the quality had a significant effect on the soil organic carbon stock variation, so this should be kept in mind when implementing agricultural practices to increase the soil organic carbon stocks. So for the rest of the work, we will calculate the 4 per mil target as using the first approach, so relative to the initial soil organic carbon stock level, in order to be in line with the land degradation neutrality objectives of the UN. Okay, so I will go to the second part. of the talk, which consists in modeling the carbon inputs required to reach a 4 per mil target using soil organic carbon models. Okay, now it works. So for that, the first part consisted in developing an inverse modeling approach to calculate the carbon input requirements. Then we applied this modeling approach to a set of multi-model ensemble. And finally, we applied a multi-model ensemble to the whole European cropland scale to provide maps of the first per mil feasibility at the European scale. So for that, we used models that are all based on this formulation, which is a system of differential equations, which basically says that the variation of soil organic carbon with time is equal to the carbon input to the soil from plant or other organic matter minus the carbon that is output from the soil from decomposition, which depends on phytoclimatic variables like soil temperature, precipitation, and soil texture. And where I here is the number of pools in which the soil is conceptually divided. So if we take, for example, the centric model, which is one of the most used models in the literature, this model is divided into 7 carbon pools, where carbon is decomposed at different rates. So for our modeling framework, first we tried to simulate the soil organic carbon stock evolution in a set of agricultural experiments. Then we selected parameters to be calibrated for each model side by side in order to fit the evolution of soil organic carbon stocks with time. And finally, we applied the inverse modeling to estimate the carbon input requirements. So to simulate the soil organic carbon stocks, basically we have to solve these differential equations. And to do that, we first need to estimate the initial conditions. And for that, which is the amount of carbon in each soil compartment at the beginning of the experiment. And so for that, we assume that soils were at steady state at the beginning of the experiment, which mathematically means that the variation of soil organic carbon with time is null. And this is a very strong hypothesis that we will see later on introduces strong uncertainties in model simulations, but which is a necessary assumption that we needed to estimate the initial carbon allocation in each soil compartment. So anyway, to solve this equation, we need to input to the model the parameter values, the meteorological data of the past decades, and then we can estimate the amount of carbon in each soil compartment at time 0. So then we introduce this information to the model together with the parameter values and the meteorological data of the experiment duration. And then we can model the soil organic carbon stock evolution with time. And then we can compare this evolution with the observed soil organic carbon stock. And in order to fit the observed soil organic carbon stock evolution, we can define a cost function that will minimize the difference between these two time series. So to do that, we use an optimization algorithm, which basically finds the optimal parameter vector that minimizes the difference between these two time series. So once we have our optimized parameter vector values, we can apply them to estimate the carbon input required to reach the 4 per mil target. And so the inverse modeling basically consists in the same scheme. So we input the parameters together with the meteorological data between 1980 and 2010, which we selected as the period of time where we wanted to estimate the 4 per mil, and the initial conditions of carbon to the model. And then we can calculate the soil organic carbon stock increase target, which, as we said before, was a 4 per mil increase over 30 years compared to initial conditions, so compared to the C0. And then now what we want to optimize is the carbon input vector. So now we can model the soil organic carbon stock evolution and calculate the difference between the soil organic carbon stock reached after 30 years using the carbon input vector input and the soil organic carbon stock target previously set. So again, with the cost function, we can minimize the difference between these two values. And we will find the optimal carbon input vector that allows us to reach the 4 per mil. So in addition to that, we also provided to the model several carbon input vectors, which were generated around the variability of the observed carbon input at the experimental site in order to provide an uncertainty bound of the optimal carbon input vector. So if we take back our Sentry model, we said before it was divided into 7 carbon pools, 4 liter pools, and 3 soil organic carbon pools, which have different decomposition rates. And where the liter pools represent the above ground and the below ground part of the plant, and the metabolic and liter pools represent different parts of the cell plant, which represent the quality of the carbon input in the Sentry model, with the structural liter pools having lower decomposition rates compared to the metabolic liter pools. And so we applied this model to, so first we input the carbon to the model, and the carbon is then transferred from one pool to the other. And each time a transfer occurs, there is some carbon which is lost to the atmosphere through CO2 emissions. And so after a certain period of time, we can calculate the organic carbon stock accumulated. And so we applied this model to 14 long-term agricultural experiments around Europe, where organic carbon stocks were measured over time, and where either some exogenous organic matter treatments were carried out, or some crop rotations were carried out and compared to a wheat-only treatment. And we ran 3 simulations to test the sensitivity of the model to the temperature. So one simulation under current climate, one simulation under 1 degree Celsius increase scenario, and one simulation under a 5 degrees increase scenario. And so this led us to some interesting results. So first, the required carbon input changes to reach the 4 per mil were 43% increase of the carbon input on average under the current climate scenario. The increase was 54% under the 1 degree Celsius increase scenario, and it was 120% under the 5 degrees increase scenario temperature scenario. And the variability across the carbon input was quite high across sites, especially under the 5 degrees increase temperature scenario. And we found that this variability was mainly linked to the amount of organic carbon that was in the soil at the beginning of the experiment. So when we compare Sentry simulations to the amount of carbon inputs actually used at the experimental site, we found that the majority of the treatments used higher carbon inputs compared to what the model was predicting to be required. And here I'm showing the additional carbon inputs used predicted by the Sentry model in this gray bar, and the amount of carbon input used at the experimental site of Feuchroll, which are these colored bars. So basically each color represents different types of carbon input. And you can see that Sentry predictions are much lower compared to the carbon input used at the experimental site. And overall, 87% of treatments use higher amount of carbon compared to the model needs. And at all sites, at least one treatment used higher carbon input, except for one site, which is the Foggia experimental site in southern Italy, which was the one where different crop rotations were compared to a wheat-only treatment considered as control. In this case, the carbon input required, according to the Sentry model, was higher compared to the carbon provided by the different crop rotations. However, there was a very high variability in the simulations, which means that the difference was not significant. And so overall, we found that Sentry predicted an additional carbon input of 0.7 tons of carbon per hectare per year to increase the soil organic carbon stock by 4 per mil. which is lower than what was used at the experimental sites on average, which was 1.5 tons of carbon per hectare per year. However, we found that on average, the experimental sites only increased organic carbon stocks by 2.5 per mil, which means that Century may be overestimating the effect of the carbon input on the organic carbon stock. And here I'm plotting the additional carbon input versus the annual organic carbon stock increase for the different treatments, which are these black spots, and for Century predictions to reach the 4 per mil, which is this red cross. And you can see that the model's needs are much lower than the regression line between additional carbon input and organic carbon stock at the experimental site. However, you can see that there is also a very high variability across sites, which was mainly linked to the different pedoclimatic conditions of the site and to the carbon input quality that was used. And in fact, Century requirements to reach the 4 per mil required a different carbon quality also. Here I'm plotting the liter pools of the Century model, and the carbon input increase that was required for each pool. And you can see that the above ground structural pool is the one that needs a major increase in order to reach the 4 per mil, which basically means that a farmer could use composted structural liter input. So for example, composting its carbon input if this is available. Okay, so to summarize this first part, we found that Century predicted a 43% increase to reach the 4 per mil target. However, the model may be overestimating the effect of the carbon input on the organic carbon stock. And thus, we decided to apply this approach to a multi-model ensemble in order to first, not to rely on one single model simulation. Second, to estimate the uncertainty related of different ways of representing the organic carbon processes. And also, multi-model ensembling is a standard practice in many disciplines like climate modeling, and it's been highlighted as an important tool to increase the reliability of model simulation. So for our multi-model ensemble, we added to Century ROTC, ICBM, AMG, MIMIX, and Millennial, which are all multi-compartmental models that have been developed over the last 4 decades, as you can see. And as such, they include different levels of knowledge that we have gained throughout the years on the organic carbon processes. And for example, the MIMIX and Millennial models, which are the youngest one, they update the contemporary understanding on the importance of the microbial activity on soil decomposition, and they explicitly represent the microbial activity in their models. But the models also differ by the number of pools in which soil is separated. They differ by the type of kinetics at which carbon is decomposed, and they also differ by the variables and processes that they include. For example, for water-related variables, some models use precipitation and potential evapotranspiration, while other models use soil humidity, and other models like MIMIX don't use any water-related variable at all. So again, we applied this ensemble to 17 long-term experiments around Europe, under the same configuration as the experiments that we previously used. And what we found was that the calibrated ensemble was able to fit the organic carbon stock evolution in the control treatment. And here you can see the predicted organic carbon stocks plotted against the observed organic carbon stocks for each model, which are these different symbols, and for the multi-model median, which is this pink line here, which you can see that almost perfectly lies on the one-to-one line. However, we found that not all the models performed the same. So here I'm comparing model performances by plotting here the standard deviation of model simulations normalized against observations. This is on both y and x-axis. And also you have the correlation coefficient on this quarter circle. So basically, on this graph, if you were a model, where you wanted to be is here, close to the observation, and where you don't want to be is here, far from the observation. And of course, the non-calibrated models were those that were performing worse compared to the calibrated models that were closer to the observation, except for one model, which is the AMG model, which is this red spot here, which is the only model that even when it was non-calibrated, it was able to fit the evolution of organic carbon stocks with time. And this is interesting because this was the only model that was not initialized using the steady state assumption. Instead, the model is initialized using observed initial organic carbon stocks. So concerning the 4 per mil target, we found that the additional carbon input required to reach the 4 per mil for each model that you can see plotted here for the non-calibrated configuration in blue and for the calibrated configuration in orange. The requirements were highly variable across models. And we found that there was a higher variability across sites when the models were calibrated, which is expected since we calibrated model parameters side by side, whereas in the default configuration, model parameters are constant. And also we found that the variability across models was lower after models were calibrated, which means that the calibration basically realigned the behavior of the models to the control treatment. And so we found that for the multi-model median, 107% increase of carbon input was required to reach the 4 per mil target, which is much higher compared to the century predictions that was only 43% increase, which shows how it's important not to use only one model and not to rely on the prediction of one single model. So to summarize, we found that the multi-model ensemble predicted that carbon input had to more than double in order to reach the 4 per mil target. However, there was a very high variability across models, which shows the importance of using multi-model ensembles. So the last part of this talk is dedicated to applying a subset of this multi-model ensemble to the whole European cropland area in order to provide maps of the 4 per mil feasibility at the European scale. So the subset, which is it's based on ROTC, ICBN, and AMG, because of time problems, we could not apply all the models to the European cropland area. And the objectives of these simulations were to predict the soil organic carbon stock evolution between 2015 and 2100 in order to estimate the carbon input change to reach the 4 per mil target in this period of time. And finally, to test statistical calibration technique of the parameters in order to try to improve the simulations of the models. So to do that, we retrieved data on soil sampling from the Lucas Surveys campaign of 2015 on around 6,000 cropland sites. And for climate scenarios, since we don't know how climate will evolve in the future, we selected 2 representative concentration pathways of the IPCC, the RCP 2.6, which predicts average global temperature increase between 2080 and 2100 compared to the period 1986-2005 of 1 degree Celsius, and the RCP 6.0, which predicts temperature increase of 2.2 degrees Celsius in the same period of time. And for the statistical calibration, so since we didn't have data on the organic carbon stock evolution at the European cropland scale, but we only have data for 2015, what we did was that we used the data that we had simulated on the long-term experiments previously. And so we retrieved the values of the calibrated parameters for each site, and we tried to link these parameter values to the pedoclimatic conditions of the sites using multiple linear regression models in order to predict the value of the calibrated parameters at the European cropland scale. So I won't go too much into the detail of this technique, but what we found was that this statistical calibration technique was able to reduce the relative error of model simulations for 2015 by 63% for the ROSI model and by 40% for the multi-model mean. So here I'm plotting just for a ROSI model the relative error between model simulation and observed soil organic carbon stocks in 2015. So you have the non-calibrated version on the left and the statistical calibrated version on the right. So basically here, the blue spots represent sites where the soil organic carbon stocks were overestimated by the models. And in red, you have the sites where there was an underestimation. And when the sites are whiter, they have a lower relative error. And so you can see that the statistical calibration was able to globally decrease the relative error of soil organic carbon stocks for the ROSI model. However, we found that this calibration technique did not improve ICBM simulations, and it could not be evaluated on AMG because, as I said before, the model is initialized with observed soil organic carbon stocks. So concerning the 4 per million targets, we found similar results for both climate change scenarios with higher carbon input requirements in Northern Europe compared to the South, and where carbon input requirements were above 150% in the North, and they were not over 40% in the South. However, we found that there was also a much higher relative standard deviation in Southern Europe, which suggests that model simulations are much uncertain in the European South. And this you can see here. Okay, so I will go to the discussion part. So we found that the carbon input requirements to reach the 4 per mil were 43% according to Century, which corresponded to average 0.7 tons of carbon per hectare per year in addition. And the carbon input requirements were 107% according to the multi-model median, which was around 1.5 tons of carbon per hectare per year, but with a very high uncertainty across models. And it was 108% increase under both climate change scenarios for the European cropland scale, which corresponded to 2.7 tons of carbon per hectare per year on average, but with a very high variability across latitudes. And if we compare our results to the literature, we found that our results were similar to the results from Martin et al. In 2021, who estimated a 42% increase of the carbon input in France croplands using the ROSI model to reach the 4 per mil over a 30-year simulation, which are similar to our Century predictions. However, the predictions from Riggers et al. In 2021 found much higher carbon input requirements in German croplands, and the carbon input requirements range between 2013 and 2083 using a multi-model ensemble under different climate change scenarios. And these much higher carbon input requirements were mainly linked to the fact that the authors were predicting very strong carbon losses throughout the century in German croplands. And if we compare our results to what is actually used in European croplands, we found from Zhang et al. That around 0.3 to 0.9 tons of carbon per hectare per year coming from livestock manure were applied to European croplands, which is similar to century requirements of additional carbon input, but which is much lower to the requirements predicted by the multimodal means. However, this carbon is already applied to the soil, so it cannot account as additional carbon input. However, Zhang et al. Estimated that only 26% of this carbon input that was produced from livestock manure in Europe was actually applied to croplands, which means that there may be some room for improvement. And also there are other sources of exogenous organic matter which are currently disposed on landfills, for example, from sewage sludges, although they're very low, and from municipal waste in Europe. It's also worth to note that exogenous organic matter additions do not provide a direct climate mitigation benefit, because it's actually only a lateral transfer of carbon that was already sequestered from the atmosphere and is brought to cropland soil. However, exogenous organic matter additions can be better managed to decrease the greenhouse gases emissions, which are associated to their storage and to their spreading, and they can be better distributed in order to locally improve soil organic carbon stocks, but not only that, also the additional organic material improves soil fertility, improves water retention, and other soil properties, which are important for food security. So a feasibility on the 4 per million target is unlikely using only exogenous organic matter additions. Instead, we will need to implement multiple practices that preserve and increase soil organic carbon stocks. For example, the implementation of cover cropping, the improvement of crop rotations, the plantation of crops that have higher root biomass in order to also stabilize the carbon more in the soil, and the implementation, the avoidance or reduction of tillage in order to improve soil quality. So from a political perspective, the priority remains to cut greenhouse gases emissions while helping farmers to build resilient systems that enable to preserve and restore the soil organic carbon stocks. From a modeling perspective, we saw that there were high uncertainties in model simulations, which were mainly linked to two aspects. The steady state assumption first, and the parameterization of the models. So the steady state assumption is, as we said before, a very strong assumption that modelers still highly rely on to estimate the initial conditions of the soil. However, it's been shown, and I showed you before with the control treatments of the experimental sites, that this assumption is often wrong, because soil organic carbon stocks are not at steady state under current conditions. And we also showed that AMG model, which is the model that did not use the steady state assumption, was able to reproduce the soil organic carbon stock evolution much better than the other models. Also, some works from the literature, like Dimassi and co-authors in 2018, showed that using observed initial soil organic carbon stocks could improve century simulations of soil organic carbon stocks compared to the standard steady state assumption. Also, model parameterization introduced strong uncertainties in the simulations, and currently default parameterization uses constant values of the parameters, whereas it's been shown that often parameter values vary with space and time. And for example, the work from Shi et al. In 2018 showed that using the whole range of parameter values that the parameters could take could introduce very high uncertainties in soil organic carbon stock simulations under climate change over the century. And this with different model structures, but this was especially true for models like Century and ROTC that are under conventional multi-compartmental frameworks. So some authors suggest to use more techniques that could improve the parameterizations of the models, like, for example, data simulation, which retrieves the information from the data and improves the parameterization. So our contribution in this sense was that we were able to estimate the uncertainties related to model simulations using multi-model ensembles. And we were able to test spatial calibration techniques of the model parameters, which could improve the reliability of the predictions. And so to conclude, I showed you that multi-model ensembles provide an uncertainty range of the predictions. However, models should be improved in order to increase the reliability of the predictions, either by improving the initialization and the parameterization, for example. And this could help to better assess the feasibility of the 4 mill under future climate change. Yet we found that the 4 mill target is unlikely without the implementation of multiple practices that enable to preserve and increase the soil organic carbon stock. So a few perspectives are that future research should focus on more local and diversified knowledge on how to preserve and increase soil organic carbon stocks, while covering understudied geographical regions like Northern and Central Africa, the Middle East and Central Asia, and while studying more diversified practices on how to increase the soil organic carbon stocks, which could help to better bind model simulations for the future. And so with that, I would like to thank you very much for your attention, and a special thanks to all the co-authors that have contributed to this work, and especially to Claire and Bertrand, and to the jury who's here or who's remotely attending this talk. And thank you very much.